When an engineer designs an industrial motor in modern CAD software, the resulting 3D model is perfectly smooth. Every curve of the stator and every edge of the rotor exists in a state of mathematical continuity. But a computer processor cannot understand continuous space. It cannot calculate a magnetic field at an infinite number of points along a smooth curve. This creates a direct paradox for computational physics. We are attempting to simulate the infinite continuous physical reality of a motor using strictly finite and discrete computer hardware. To resolve this, engineers rely on finite element method software, such as ANSYS Maxwell or JMAG. These programs operate as translators, converting continuous physical reality into a language the CPU can process, discrete algebra. To perform this translation, the software aims for the algebraic target, a times x equals b. When you hit the Simulate button, the software initiates a 4-step pipeline designed to build, solve, and decode this matrix equation. The first step in the pipeline is discretization. This executes the millisecond a simulation begins. The software breaks that smooth CAD model into thousands, sometimes millions, of tiny, simple geometric shapes. In three-dimensional space, the primary building block of this new geometry is the tetrahedron, a simple 4-sided pyramid. The sharp corners of these tetrahedrons are called nodes. These nodes are critical because the computer will only calculate the physics equations at these specific, isolated points in space. The volumetric space trapped inside the tetrahedron itself is called the element. Because the software only knows the physics at the corner nodes, it treats the interior of the element as a simple interpolation. It averages the exact values from the surrounding nodes to fill in the blank volume. The user can control mesh density. If the mesh is too coarse, the interpolated averages cover too much physical distance. The resulting math is incorrect. Discretization forces a compromise. To get accurate math, you need tightly packed nodes, but drawing a finer mesh consumes more computer memory. Once the continuous model is broken into discrete pieces, the software moves to step 2, assembly. Here, the geometric mesh is translated into linear algebra. The math relies on populating the variables for the target equation, a times x equals b. It does this by evaluating every single node in the mesh, one by one. For each specific point, the software identifies the surrounding material, such as copper wire, electrical steel, or air. It takes the physical properties of those materials, like magnetic permeability and electrical conductivity, and converts them into raw numerical coefficients. These coefficients populate matrix A, a gigantic grid storing the mesh layout and material properties. Next, vector X represents the unknowns we must calculate at every node. Finally, vector B holds known source inputs, like applied voltage. Because of how this assembly works, every single node in your 3D model adds a new row to this matrix equation. An industrial motor simulation often contains millions of individual nodes. By the time assembly is finished, matrix A becomes a grid measuring 1 million rows by 1 million columns. The assembly phase concludes by converting the physical 3D model into this single, massive algebraic system. Now we reach step 3, the solver. This computational phase consumes up to 90% of the total simulation time. The solver has one objective. It must invert that million by million matrix A to solve for the unknown values in vector X. Standard mathematical operations fail at this scale. The processor requires specialized algorithms to manipulate a matrix of this size. The first option available to engineers is the direct solver. It uses brute force linear algebra to calculate the exact inverse. This method is highly accurate, but it requires immense amounts of RAM to hold the calculation, often exceeding the limits of standard engineering workstations. When a matrix is too large to hold in memory, the software relies on a second option, the iterative solver. Instead of calculating a direct inverse, the iterative solver starts by making a mathematical guess at the correct values for vector X. The algorithm checks its initial guess against the matrix, updates those numbers, and repeats the loop millions of times. The algorithm continuously refines its guess until the margin of error drops below a specific threshold. When the guesses get close enough to the true answer, the software accepts it, a state known as convergence. But if the original mesh was drawn poorly, or the physical geometry is highly irregular, the iterative guesses will fail to settle. the solver will fail to converge, and the simulation crashes. The solver phase is a process of mathematical optimization, strictly limited by the efficiency of the algorithm and the capacity of the hardware. When the solver finishes its loop, it outputs the completed X vector. At this moment, the data is virtually unreadable. It is millions of raw numerical values attached to invisible points in a digital void. To make sense of it, the software initiates the final step of the pipeline, post-processing. The post-processor translates those raw algebraic numbers back into understandable physical phenomena. It starts by calculating the gradient between the raw numbers at each node, which allows the software to determine physical metrics, like magnetic flux density. It can then integrate these local gradients across the entire physical geometry to calculate macro-level forces, like the torque of the motor. Finally, the software interpolates these thousands of vector fields, smoothing them out into the recognizable heat maps used to evaluate the design. Engineers rely on these colorful heat maps, which represent the highly processed visual result of a massively complex discrete linear algebra equation.